Well, no, I'm sure. We've been, yeah, we've been this year.
Right.
Like,
What? I don't see the.
Maybe I want to come play by. Why can't I? You asked me this week, like,
What happened to the rest of it?
what?
What?
Yeah, it's-
Oh.
Yeah, I have this and I'm working.
Okay. Sorry, it took a little while. All right.
So for.
Who has not been able to access Tech Wizard yet? Everybody else was able to get, no, raise your hand, it's fine, don't be shy. You weren't able to access it yet. So what issues are you having still?
So mine, it's like, it's almost like it was still low. Then I want to let me hit like log in to then take my admin.
Same here, same here.
Same issues. Okay. I'm so sorry for this frustration. This has never happened before. We never had these issues before. So here's what we're going to do. We're gonna cancel lab report for this lab. Huh?
For everything.
For everyone. For everyone. So equal treatment, But here's the thing. I still want you to produce these labels. Whenever you're able, was to continue to figure out this. When you have your labels, 5 labels, okay? The yogurt formulas, 4, and the cookie. Whenever you have those labels, send them or submit them via the assignment. So we will tell Brittany to change it from a lab report to just labels, and you'll get your 25 points for the request. Huh?
You saw extra credit for the.
Yes. If you submit your, thank you. He's
I
ahead of
I
you.
actually know I said it and then you called on him.
Oh, so
Right, I said, how about that extra
Yeah.
credit? I said, no, I got you.
Yeah.
Yeah.
Sandra, really wanted you to know that she got you. Okay, all right. So, yeah, submit that, you'll get your 2 extra. But I don't want you to worry about lab reports and due dates because next week you have this week's lab report. So I'm so sorry, really, about this. I don't know why they messed up this year with us. Anyway, but do get the experience. Even if you don't get it this week, whenever you get it, so that you get your 25 points. We will, if you have your labels already, go ahead and submit them, get that out of your way. If you don't, the 7 of you that don't have them, whenever you have them, so that you get your grade.
So where do you submit the
Say that again.
Where do you submit the
So there will be the assignment on Canvas for the labels. Brittany will change that from report 1 to labels.
Oh.
Interesting. She'll make that very clear for you guys. Okay. All right. And then there will be a due date regular, but even if you don't have them now, we won't deduct any point for late submissions, okay? But I need you to get that experience.
And then you don't want the table of the comparison?
No, nothing. I don't want anything anymore. That's the link. I'm tired of this. Okay, just the labels. All right. Are we ready? Happy Monday, you guys. All right. What is a sampling plan? You know, this is the most boring lecture topic, but we'll get through it together. What is a sampling plan? Go ahead. Great.
Like,
from the steps you take from the beginning, the sampling, so like how many samples you're
Yes.
gonna take, when you're gonna sample,
Yeah.
to all the way to when you're actually testing the sample. So
Absolutely.
like storage.
Thank you, absolutely. So starting with determining how many samples, what's your sampling process? Any transportation, storage, sample prep. So everything that goes into the beginning to the time that you're going to do your testing, everything. Okay. Why is sampling plan important? If we mess it up, that's going to happen. So you think?
If brain users so like your analysis will be great.
You'll make the wrong decisions. You're gonna just get erroneous data and then you're going to cause your company to lose millions of dollars, or you're gonna cause illness to millions of people. So it's really bad. The worst thing that can happen is to have bad sampling. Okay. These gray ones, you will review later after we're done and while you're studying. Make sure you know these. Okay, we have two types of sampling, attribute sampling and variable sampling. Attribute sampling is for something that is randomly distributed. Let's say you have a mold growth, and then you have aflatoxin due to the mold growth. You don't know which part of the food has the mold on it. It's random. It could be anywhere. So this is what is attribute sampling, is sampling you do when you have a certain characteristic that can be anywhere in your food, not distributed evenly. Okay? So anything that is not distributed homogeneously or evenly across your sample or your population. When this happens, when you're looking for an attribute like aflatoxin or Clostridium botulinum, for example, you have to take very many samples because you don't want to risk it. So you want to take a lot of samples from your population just to make sure you cover your basics. Because you don't want to miss aflatoxin, you don't want to miss anything that could be harmful. So you take a large sampling size, so a lot of replication. That means a lot of samples you pull out from the population, and then you are checking the presence or absence of a variable, and then you decide acceptability. Clostridium botulinum in canned food, or aflatoxin in nuts, for example, in a population of nuts. And then whatever that attribute is, sometimes you're just looking for positive or negative. Sometimes you're looking for a count. So you don't want to have any aflatoxin. You need to have a 0 concentration. You don't want to have any Clostridium botulinum. You want it to 0. So if you have any amount of those, you reject the lot. Unless you have a minimum acceptable level or maximum acceptable level. And if it's below that maximum acceptable level, then you pass the lot. Variable sampling, that's when you have something distributed evenly or normally, like percent fat or moisture content. So that is distributed evenly in your sample. So we call this variable sampling. And here, since it's normally distributed, you don't need to take that very many samples. So a smaller sample size compared to attribute sampling. Okay, so your N or number of replication is less. And usually it's a quantitative characteristic. So like I said, moisture content, fat content, total sugar. So something that you can quantify, and it has a continuous scale. And then you decide acceptability based on reference and you know what it should be. So you decide whether or not you let it pass. Is the moisture high? Like, for example, in wheat, we control moisture content so that you don't have mold or mold growth during storage, so it shouldn't be any more than 10 to 12% moisture, if I remember correct. So you determine moisture content in wheat and determine acceptability, or maybe dry it a little more before storage. Yeah, so these are some examples. All right, sometimes selection of sample size depends on overall quality and sampling cost. So you take into account how much is going to cost me if I have 10 replications versus 50 replications. So things can, other factors that can play a role in deciding on your number of replication. In other cases, you don't have very many choice. If it's nutrition label, you have to have 12 replications or samples pulled out randomly. And then you form a composite. So you take those 12 samples, you make it into one big sample, and then you have 6 sub-replications. That's what you need to do for nutrition labeling. That's a government regulation. You don't have much choice there. This section, the single, double, and sequential sampling, was removed from the chapter in your this new edition. I wasn't sure why it was removed. I was looking at it, I was like, why did they take it out? Okay, but anyway, I'll just go over it briefly, FYI. Sometimes you take one set of samples, N, okay? N set of samples, and then you have an expected value or a quality that you, after you do the testing, you expect to have a specific characteristics. If it doesn't meet that number of defects, for example, if it has more than a specific number of defects, you reject. If it has less than a specific number of defects, you accept a lot. Double sampling sometimes happens when your value is between rejection and acceptance. You do another set of sampling until you're able to make a decision to reject or accept. That's double. The sequential is a little bit more complicated. So you take samples and you measure for a specific attribute or variable. And if the value or number of defects fall somewhere in the middle, you continue sampling until number of defects are higher than the specific allowable number, then you reject, or you fall in this region where you accept in the bottom. So it's a little bit complicated. I'm guessing that's why they removed it from the chapter. It's not a very common, sequential sampling is not very common. Okay, let's look at this. When monitoring food safety by measurement of mycotoxins, many randomly selected samples are required. A single sampling plan is required. Sampling error is many times greater than analytical error.
And see.
It's all of the above. So you determine I'm going to take 20 samples and then to cover your basics. And if you get one positive, you reject. You don't need to measure again because you're not allowed. You don't want any aflatoxin in yours. Okay. So we always, when we make a decision, we're never 100% sure that our decision is correct. Never. There's always a chance of error. So there is a consumer risk and there is a vendor risk. For the consumer risk, you want to make sure that your error is less than 5% chance of being wrong. You want to protect the population. When it is vendor risk, rejecting a lot and losing money for rejecting a lot, your error can be higher, like 5 to 10%. But also you want to be very careful. Above than 10% is really risky from losing money standpoint. So usually your sample plan should be as simple as you can.
have it flexible where you can make changes as you go if needed, protecting both consumers and vendors, and your results are reliable. So, in a nutshell, basically. There are AOC methods in the book, give a lot of examples, but in order, let's say, to sample from a bag of flour, let's say your lot has 100 bags of flour, you take the square root of that number of flour bags. So if you have 100 bags, you want to select 10 bags. And then how do you select them? You have different ways of determining. Have you, do you know the random numbers? A table of random numbers. So you would usually have a table of random numbers and you number your bags with random numbers, and the table has all of those random numbers. You number the bag, close your eyes, randomly select, or let the computer do it for you. So select random numbers and go grab the bag that has those random numbers. And then once you have the bag, from the bag, the center of the bag, you take the diagonal point, and then you take the one across from it and make a composite. So from every bag, you take from two diagonal points opposite to each other, and you combine them, and then you will have a sample from each bag. So when your sample is homogeneous, like flour, it's easy. You take a sample and you move on. When your sample is heterogeneous, like it's a food product with different layers and different sections, you have to take samples from multiple locations. Oftentimes, we homogenize our sample before taking out a sample. And we'll talk about that later on when you, let's say you have a chewy bar. You're doing a capstone project and you have a chewy bar. How do you take a sample for analysis from a chewy bar? What would you do? Of course, every region, one has a chocolate chip. This region doesn't have a chocolate chip. There's a nut. This side doesn't have a nut. What do you do?
Put it in a blender.
You put it in a blender, but isn't it a blender well for you? Then gooey, chewy. What do we do? What is the trick? Huh? Diluted in water. No, that's gonna be enough.
You just do multiple reps of like cutting the bar up, so then you get a better view of the whole bar.
You could, but what is another way? Have you heard of tire grinding? Freeze it. You freeze it and grind it with frozen. Wait, sometimes we put, what do you call that ice? CO2 ice. What do you call that? Dry ice, right? Yes, and then you blend it so that it doesn't, like, the fat doesn't ooze out, the moisture doesn't ooze out. So it is well homogeneous sample, and then you put replications on. So you can do manual sampling when you are working in a plant and you have products coming out of the line. You can manually take out sample prone to human error, or you can have a mechanical drawing of a sample. Less biased. They do that with milk, for example. So there is a unit that you can withdraw a select sample of milk every unit time, and that sample get analyzed. So there is non-probability sampling and probability sampling. You always want to go with statistics and do probability sampling unless you have limitations. Like in this truckload of grain, how are you going to do random sampling and numbering each grain, give it a number? That's impossible. So there's no way of being able to do statistical sampling here. So
usually an experienced personnel will judge and take samples from different locations. Sometimes you have restricted sampling. Let's say you have a silo and you have all these grains. You can't reach to the bottom to get a sample from the bottom. So you just have to, whatever is convenient to you from the top, take sampling. So this is nothing you can do about it. Probability sampling is what we normally try to follow whenever possible. And we have the random sampling that I just told you. Let's say you have bags of flour. They smelled the smell and left. No? Okay, so the bags of flour or cans of food, you can, or boxes of food, you can give them random numbers and have the computer spit out some random number and pick those out as your sample. Systematic sampling is the example of giving, every time point, every 5 hours, you pull a sample. So you kind of time your sampling in the line of production. Stratified sampling, the book gives you an example. Let's say you're a company and you have tomato soup plants. So you give every tomato soup plant a number, and from there, the production in that day, you do random sampling and take a sample, and then you will be measuring samples in each production plant. So the cluster sampling is same as stratified. So you number your plants and randomly select, let's say if you have 10 plants, randomly select 3 plants for assessment. They're all following the same protocol to produce the tomato soup. So you randomly select 3 plants and then apply random sampling on that plant production as well. Composite sampling is like the example I gave you for nutrition labeling. Take out 12 samples or however many samples, formulate one composite sample and do subsampling for analysis. And the selection of the 12 samples or how many samples would be randomly selected. So the following are potential problems associated with sampling that may result in reduced reliability. Non-statistically viable convenience, like you can't reach certain areas in your lot. Poor storage conditions, mislabeling of samples. Jordan. All of the above. All of these are bad. Poor storage conditions will change the characteristics of your product, and we'll talk about storage in a little bit. Mislabeling, that's the worst that can happen, is you take a sample and you label it wrong, or yeah, that is the worst that can happen. Yes, absolutely. Yes, yes. Restricted here, yeah, like the restricted sampling, a silo or a truckload, you can't reach the bottom, you just take sample from the surface. So that could potentially cause error. What if the sample on top is good or bad, and the sample at the bottom is not?
When I've seen these trucks do that, they have a fancy bucket that goes in a certain degree, comes out, tips. and
Yeah.
that's it,
Yeah,
As the truck drives in.
exactly. So, but it has its limitation, and we cannot call it random selection or probability based. We talked about particle size or cryogrinding, but particle size of the sample is very important. So one time I walked into a capstone group doing fat analysis, and they had their product was potato chips. And one of the assays that you do for fat analysis is called the Medina. And you have a very special flask, funky looking flask, where you put your sample in and you add all of your reagents and you shake to extract the fat using organic solvent. And when I walked in, so I saw this flask and I saw a couple of big pieces of potato chips. Like
the way they are. And I was like, what are you guys doing? Extracting the fat. How are you extracting the fat from this whole potato chips? No. You can't do that. You have to reduce the particle size. You need to mill your sample, and not only mill it to a specific mesh number. What's the definition of a mesh number? It's how many holes in a linear. Yes. So the more holes you have in a linear inch, the bigger the mesh number, the less is the particle size. Okay? So for analysis of moisture, protein, or mineral, 20 mesh is enough. If you are extracting, like for fat analysis, we're extracting the fat from the sample and weighing the fat. So you really want to reduce that particle size as much as possible, and the recommended is 40 mesh. So for certain assays, we need a smaller particle size to enhance the efficiency of the extraction or of the analysis. So cryogrinding, we talked about it when you have a sample that has very high moisture content or very high fat content or really sticky. So you really want to freeze it, grind it, frozen, so that you don't have the issue with stickiness, losing moisture, losing fat while you're grinding. Let's see. So there are equipment like this rototap that will help you separate particles based on their size using sieves. Why do we need to eliminate enzyme activity during storage of sample? Sometimes you prepare your sample, but you're not able to test today. You have to store it until you have time to do the analysis. So what enzymes do we have for that, and why do we want to not do it?
The enzymes could change the catalysis of your sample.
Exactly.
They break down.
Yeah.
the compound.
Yes. So if you have endogenous lipase like oxygen, and you are preparing the sample to determine liquid oxidation, if you store it at high temperature, if you store it with oxygen permeability, if you store it, I don't know what else, with light, abuse of light and temperature and oxygen, and then oxidize the liquid. And when you do analysis, you're going to see liquid oxidation that wasn't really originally in your sample. So you don't want enzymes to work. Sometimes we have endogenous proteases. So you're looking at the protein characteristics, and you have proteases broke down the protein. You do not want enzyme activity because it changes the chemical composition, it changes the characteristics of your sample. How do I stop enzyme activity? Cool it down, store under refrigerated conditions. Yes. What else? If heating doesn't, go ahead.
I was gonna say either high heat or acid.
Exactly. So high heat or acid, if the heating is not going to impact the assay that you are going to perform, you try to inactivate or change the pH to where the enzyme is not active. Okay, I'm storing. How do I avoid lipid oxidation that is not necessarily enzymatic? Because there's lipid oxidation that can be due to lipoxygenase in the sample. But what other factors?
Opaque container and or flush them out.
Aha.
Container.
Flush with nitrogen. If you are storing and you're worried about lipid oxidation, flush with nitrogen. That means the nitrogen replaces the oxygen on top of your sample before you close it. So try to get the oxygen out. Make sure you don't have oxygen permeability. Make sure it's away of light. Temperature abuse. Don't store it at high temperatures. Sometimes you can add antioxidants in there as well.
Limit microbial growth or contamination. Why? What happens if you have microbes growing? What?
They're eating and changing the product.
They're eating. They're just eating your starches and their your protein, your fats.
Great example is sampling kombucha,
Kombucha.
because it's a live active product on the shelf, and if you sample it 1 month post shelf.
So it has
Change-
less
They'll
stuff.
have more alcohol,
Have more
it'll
alcohol.
be illegal now.
Who likes kombucha? I don't. Okay. So we don't want microbial growth. It's going to change your characteristics of the product. Definitely. How do we stop that or prevent that?
Can roll in another activity.
So- Yes, you can, absolutely. Sometimes we dry our samples, make sure we know what the moisture content is, so that if we determine protein or fat or whatever, we use the moisture content to convert to as is basis. So drying and then storing, that's good. What else? Proper packaging, low temperature. You can change the pH if that's not going to impact your analysis. Yeah, so you want to do what you need to do, whether it's through you can also add antimicrobial agent as well. Yeah, very good. Well, whatever you do, avoid sample alteration. That's kind of the take-home message. Now, for a +5, solve this question and bring it to class next Monday on a piece of paper for extra credit. You don't have to do it. It's good exercise. You get +5 if you do it. Next Monday. Yeah. Write it down. If you want to do it, it's up to you.
It'll be fun, this will be on the campus, so
Oh, well, my slides are on Canvas. And this is question 7 in your textbook as well, in chapter 5. Yeah. Okay. Phew, done with this subject and questions. What?
never have to think about it again.
It's only in exams. All right, so we can start a really, in my view, fun topic. Unless you don't like chemistry and calculations. Where is it now? Hmm. So, yes. What's that? What do you mean? Week 3 is not open to students. I did post them on Friday. Didn't I make it visible? What did I do? Let me see.
Brain probably.
Look at week 3. I have a green arrow. All right, let me show you what I'm seeing so that you don't think I'm crazy. All right, so this is week 3. Where are the modules? Modules. Week 2. Week 3. Oh, look at that. Sorry, you guys, I didn't publish the modules, I published the lecture material. Ah, it's the TA's fault. Saj, what have you done? What's that? I didn't say Brittany, I said all the TAs. That's the easiest way out. Blame somebody else. Okay. So now you have it, all right? Okay. So in analysis, working in any lab where you're going to do chemical analysis, you have to prepare reagents and sometimes buffers. So we need to remember the ABCs of equation equilibrium, molarity, normality, number of moles, molecular weight, all of this stuff or jazz, as we want to call it. So you won't be able to prepare reagents if you don't know these concepts. So what we're going to do is go back to the very beginning and review some of these concepts with you. And in lab next week, you will be preparing the agents that you will be using in different future labs. So this is the theory and the calculations. What I want you to do is take out a piece of paper, now write your name on it, and use it for calculations. You want to show your calculations to get your +2. I know that some of you turned in to Nigel the other day. What was the issue with some of the papers? Listen to Nigel.
Yeah, it was just like, that is not enough, like, you wanna show your words, your calculations, how you get to the picture rather than writing it down. That's how you go to
Back sheet or full sheet?
You're going to need multiple sheets. Yeah, well, start with one full sheet today now, because there are going to be a lot of exercises. Yeah. So basically what Nigel said is when you write your name, and then we're solving questions, don't put justified an answer. Show your work. We're not really grading them like correct or not correct. We want to see that you did the work and you'll get your +2. Before you turn it in, take a picture of it so you have your own calculation, okay? All right. Let's try to remember a few concepts about buffers. What is true about a buffer? A mixture of weak acid and the conjugate base. Has a neutral pH, or it stabilizes a certain pH, or all of the above. Mitchell. A and C. That is correct. Of course, buffers can exist at any pH, not neutral pH. And it is a mixture of a weak acid and its conjugate base. Conjugate base is another word for it that you will hear it, is dissociated acid. So when the proton is lost, it becomes a conjugate base. So you have the protonated acid and then the deprotonated acid, which is also known as conjugate base. When they both exist in the system, you have a buffer. And we'll have a lecture on buffers later on. But that's what I want you to remember just now. Okay, and buffers stabilize, they stabilize pH. So let's say you have a buffered system. So you have acid, a weak acid, and its conjugate base in the system. And let's say you are titrating into a buffer with acid. So you're putting down acid. What does the acid have as protons? You have protons. When you're titrating and it's with an acid, you're titrating with having protons. And in your buffer, you have the conjugate base, and then you have your weak acid. So your conjugate base is an A minus, dissociated, deprotonated, and the AH is the protonated acid that has the proton there. When you're titrating, what's going to happen? This conjugate base is going to pick up the proton and bring back the pH up. So the proton goes down, the pH drops a little bit, the A minus picks up the proton, balances the pH, resists change of the pH. The opposite is true. If we are titrating with a base, OH minus, a base, this is going to be picked up here. The protonated acid will give up a proton, then you'll have H2O, then your pH adjusts again. Okay, so resisting change in pH, whether you're adding acid or you're adding base. Okay, so let's remember some of concentrations. You'll be working a lot with these concentrations. Molarity is number of moles of solute per 1 liter of solution. And number of moles equal mass over molecular weight. Okay, so N is for number of moles, and the unit is moles. And then liter of solution usually is your volume in liters. And then your mass is in grams, and molecular weight is grams per mole. So if I put the units, then it makes sense to you. So what this is saying is molarity equal number of moles per volume. Here is 1 liter, the unit. Here is moles, the unit. So moles per liter. Number of moles equals mass. This is in moles. This is in grams. And the molecular weight is grams per mole. So just jot that down so that you remember whenever we solve an equation, you always need the units. And if you know your units, you know that your equation is correct if your units cancel. Okay, so units are important. Normality is number of mole equivalent of a solute per liter of solution. What does that mean? If you have an acid, let's say you have HCl. If you have HCl, this is 1 H. So you have 1 is the number of equivalents or number of mole equivalents. If you have H2SO4, like in this example, you have 2 H's. So your number of mole equivalent is 2. That's why normality of H2SO4 is always double the molarity, okay? Because normality equals X, which is number of mole equivalent of solute, times molarity. The X for H2SO4 is 2. The X for HCl is 1. So normality of HCl equals molarity of HCl. Always. Same with NaOH. Normality of NaOH equal normality or molarity of NaOH because you have 1 OH. If it is, let's say, calcium hydroxide. Calcium hydroxide, you have 2 OH. So the molarity equals twice the normal, 2N equals 1M, basically, for calcium hydroxide. Equivalent weight, that means the molecular weight divided by number of mole of equivalents. This is relevant in a later chapter when we determine percent of organic acid, when we determine acidity organic acids, they have multiple carboxyl groups, so they have multiple H's. So when we are determining the concentration, we need the molecular, the equivalent weight, not just the molecular weight. So this will become relevant later on. Percent, it is a ratio grams per 100 grams or milliliter per 100 milliliter. That would be a percentage. And sometimes concentration is really, really low, less than 1%. So then it becomes parts per million, like milligrams per liter or milligrams per kilograms, or parts per billion, micrograms per liter or kilogram, or parts per trillion, nanograms per kilograms or 1 liter. So depending on how dilute the sample is, we use appropriate unit. Equation of neutralization. You're familiar, do you remember? When we're balancing an equation, we say milli equivalent. Let's say if it's acid-base reaction, milli equivalent of acid equal milli equivalent of base. So milli equivalent of one reactant is equal to milli equivalent of the other reactant. And milli equivalent equals milliliter times X, or milliliters of X, sorry, just to clarify. Usually you see it like that, N by volume equal N by volume, or molarity by volume equal molarity by volume. And if it's milli equivalent, the volume is in milliliter. Okay. So this can be very helpful if we are doing dilution. So let's try to practice. You want to prepare 1 liter of 0.1 normal HCl from 12 normal HCl stock solution. And 12 normal is the concentration usually we get when we buy HCl from the vendor. The bottle is, the HCl in the bottle has 12 normal HCl, very, very concentrated. And often we need to prepare much dilute acid. Very common is 0.1 normal. You will be using that in the lab for multiple experiments. So go ahead. Tell me how would you prepare 1 liter of 0.1 normal HCl from 12 normal HCl stock solution. Use your paper, apply the equation, and tell me how you do it. Yeah, 1 more minute, and then I'll let you go. Let's solve this, and then I'll let you go. Anybody with an answer? Graham, do you have an answer? Yeah, tell me. What's your unit? Liter. Yeah, correct. Let's see how you solved it. Okay, so you need to prepare 0.1 normal, which is also molar as well, right? Whether it's normal or molar, it doesn't matter. And then you need to prepare 1 liter of that. So you're solving for X liters, and then you have the 12 normal. So how many milliliters or liters I need of the 12 normal to prepare 1 liter of 0.1 normal? It's better
to convert this to milliliters. So I would say 1,000 milliliter, just because this is really, really dilute compared to the original. So 0.1 normal, or I would say number of moles per liter. And then I'm solving for X in milliliter times 12 normal. Anyway, I can keep it normal because it can cancel each other. Then I would say it is 100 milliliter times normal divided by 12 normal. The unit cancels, and this gives you 8.33 milliliters.
Okay, so what do you do next with this 8.33 milliliters? And you're in a lab, you figured this out, and then what? Tell me. Go ahead. What do you do?
You will add the 8.33 in the volumetric flask enough in the 1 liter volumetric flask, and after they will fill the PV.
Exactly. All right, so you would get your 1 liter volumetric flask. Never add water to acid. It will not a good thing. If it splashes the acid in your eyes, that's not a good thing. Fill half of it with DDW, distilled water. And then add your 8.33 milliliters of acid, and then make up the volume with DDW. And then now you have your 1 liter of 0.1 normal HCl. Whenever I say in an exam or a quiz or anything, how do we prepare this solution? Don't just give me the volume, just tell me what the procedure is. Okay. Sorry, you guys, I kept you 5 minutes, but there you go. I'll see you on Wednesday. Keep with you, because once we're done with all calculations, you turn it in. Keep it with you till next time.